Agentic AI operates differently from a standard chatbot. It relies on iterative reasoning loops, allowing the model to independently plan a task, execute it, and evaluate the result before moving to the next step. But this capability introduces a severe engineering flaw when built by novices. The standard unoptimized approach is to feed the full system prompt and the entire accumulating chat history back into the model for every single turn of that loop. This is a chart plotting agent iterations on the x-axis against token volume on the y-axis. What starts as linear task progression compounds geometrically into massive token consumption. In enterprise architecture, we call this specific, unscalable failure state the God agent anti-pattern. It forces a single monolithic set of instructions to handle every possible scenario. Because of this compounding math, merely tweaking your prompts is insufficient. Left unchecked, the system quickly degrades from a highly productive tool into an uncontrollable financial liability for your cloud operations. Mitigating this runaway token burn requires entirely dismantling the monolithic agent design. Token management can no longer be treated as a post-deployment developer afterthought. It must be engineered from day one as a rigid pillar of enterprise Cloud FinOps. To decouple AI capabilities from exponential cost scaling, you need a specific structural blueprint. The ONEITWORLD framework establishes this architectural pipeline. This framework forces engineering teams to change their underlying assumption. LLM tokens cannot be treated as an infinite, cheap utility. They are a scarce, finite cloud resource. Securing a viable benefit-to-cost ratio for enterprise-grade AI deployment mathematically requires adopting this strict six-pillar approach. The architectural breakdown begins at the absolute start of the data flow, aggressively controlling the input payload. The first pillar is context pruning. It corrects the fallacy that an LLM needs global, untargeted context to make a single local decision. Instead of dumping a complete chat history, engineers must implement sliding context windows, semantic retrieval, and intelligent summarization. These mechanisms guarantee the model receives only the exact, minimal set of data required to complete its immediate next step. Filtering the incoming data is only half of the input equation. The system also requires the structural separation of the tasks themselves. This leads to the second pillar, clean architecture. This physically dismantles the God agent anti-pattern we identified earlier. In an agentic context, clean architecture means breaking complex macro tasks down into highly specialized, single-purpose microagents. These microagents follow the governing software rule of high cohesion and low coupling. By separating concerns, each microagent utilizes a much shorter, tightly focused prompt. This imposes rigid, predictable boundaries on token limits. Pruning the context data and modularizing the agents work together to choke off the exponential growth of inputs. This establishes a mathematically bounded foundation before any inference even begins. Once the input payload is restricted, focus shifts to optimizing the actual compute resources expended during inference. The third pillar is adequate model routing. A common, costly flaw is assuming every action in an agentic loop requires a massive, state-of-the-art LLM. The FinOps mandate requires routing simple tasks, like data extraction, basic formatting, or classification, strictly to inexpensive small language models, or SLMs. The heavy, highly capable frontier models are strictly firewalled. They are triggered exclusively when the pipeline requires complex logic gates or high-stakes reasoning. Beyond selecting the model, optimization must also target the external interfaces the system uses to act, tool calling, and function schemas. This brings us to the fifth pillar, lean tool descriptions. In function calling, there is a hidden architectural tax. Developers pay for the token weight of a tool's definition during every single conversational turn. To eliminate this waste, tool schema descriptions must be surgically lean. They need to be stripped of verbose language and injected into the system dynamically. The strict rule here is absolute. If a microagent does not need a specific tool for its current phase, that tool's definition must be entirely excluded from the prompt. By deploying dynamic model routing and lean schemas, the compute layer transforms from a flat, expensive baseline into an elastic, strictly needs-based expenditure. The ultimate FinOps optimization goal is bypassing the LLM inference step entirely, reaching the necessary response with zero token cost. This is the fourth pillar, semantic caching. It forces us to ask a simple economic question: why pay the cloud provider for the exact same answer twice? The caching sequence works in 3 steps. First, the system intercepts the incoming user query before it is ever routed to an LLM. Second, it generates a vector embedding of that query. This maps the mathematical intent and context of the user's request. Third, it executes a similarity search against a vector database that stores all previous system responses. If the system detects a high-confidence semantic match, it retrieves the historical response and serves it directly to the user. The economic truth of a cache hit is stark. The model is bypassed entirely, dropping both the token cost and the compute latency for that specific action to absolute zero. Semantic caching represents the purest form of token optimization, eliminating redundant iterative cycles right at the infrastructure level. Deploying an optimized pipeline is only the first step. Even the most perfectly modularized and routed systems require aggressive, ongoing governance in production. This introduces the 6th pillar: token monitoring. It is an unbending engineering maxim that you cannot optimize what you do not measure. The architecture requires dedicated observability layers to trace token burn across all levels. The primary goal of this granular observability is to instantly identify runaway iterative loops silently draining your budget, long before the billing cycle ends. Granular observability prevents cost spikes from being a monthly billing surprise. It turns those potential liabilities into immediately actionable engineering metrics. When we step back, we can evaluate the fully assembled 6-pillar architectural pipeline in its complete operational state. Compare the disastrous initial baseline, a monolithic system endlessly dumping its entire history into a single model, against the structural precision of this framework. Pruning and modularization choke the incoming data. Routing and schemas optimize compute, and caching bypasses it entirely. This structural shift alters the unit economics of an agentic AI solution. It breaks the geometric curve of compounding token consumption. The financial savings are massive, but this rigorous approach to token engineering also drastically reduces systemic latency and improves the AI's contextual accuracy. Building a basic agent is easy. Engineering that agent to survive the mathematical realities of cloud economics is where true enterprise architecture begins. Mastering token engineering is the definitive baseline for taking AI out of expensive digital experiments and deploying it as a scalable, high-impact asset.